Okay, so we have come to the last section of this chapter on differentiation, and this one is about L'Hopital's rule or L'Hopital's rule. We are all familiar with this rule from calculus. We use this rule to calculate many limits which are otherwise somewhat difficult to calculate or difficult to figure out how to calculate such limits. But at the time of using this rule in calculus, we did not really care about whether the rule is applicable to a limit or not. We did not really care about the hypothesis that must be satisfied. But now we want to rectify that. So there are two versions of this rule that are considered in this text. This is the first version. So let's see what it says. We have a subset X of R and we have two functions f and g, both real valued and having X as their common domain. Also, we are considering a point x0 in X, which is also a limit point of X. It's a point in the domain as well as a limit point of X. Now, what are the conditions on f and g? F and g both vanish at that point x0. They are both also differentiable at that point x0, and the derivative of g at x0 is non-zero, it does not vanish. Okay, so these are the hypotheses. Then the theorem concludes, or rather it's a proposition. The proposition concludes that there exists a positive real number delta such that there are two parts of the conclusion. The first part says that the function g does not vanish in this set. And the second part says that the limit of the ratio of f and g values at that limit point x0 in this set exists and is equal to the ratio of the derivatives of f and g at x0. Now some observations about all these things. Note that we need x0 to be a limit point of x because we want to be able to talk about the derivatives of f and g at x0. We know that we can only talk about the differentiability of a function at a point in the domain which is also a limit point of the domain. That's why we need x0 to be a limit point of x. And the reason for taking this is clear because it's going to appear here in the denominator. What else is there? Oh yes. Why this delta though? I mean, because g vanishes at x0, is it not enough to simply remove x0 from x and have the set this and consider the limit in this set? No, you see, we are given that g vanishes at x0. So removal of simply x0 from x may not be enough because in this set also g may vanish somewhere else. So what the theorem concludes is that yes, you have removed x0, but then you also have to concentrate your attention very close to x0. A little to the right of x0, a little to the left of x0, but at the same time, always being inside x. Everything that is available in this open interval may not be a point of capital X. Okay, capital X may have some gaps in it, so that the original x0 is sitting inside x, which we have removed. But when you go to the right of x0 or to the left of x0, you may not be able to go continuously, like what we can do by being inside this interval. X may have some gaps in it. So that's why we take the intersection. And that is necessary also. You see why? because we are talking about the limit of this ratio, right? So whatever x we are going to consider from here must after all be points in the domain, otherwise fx and gx will be meaningless. That's why we need to intersect with x. Now this proposition is not proved in the text, so it will be done in the exercises. So we are also going to leave it like this for now. When we solve the exercises, we will see the proof. There is one more issue though, before I leave this completely. Fine, so we have understood the entire interpretation of this limit, but you also keep in mind that you can talk about the limit of a function at a point which is an adherent point of this set in which you are considering the limit. So while proving this, you have to also address that thing, that is x not an adherent point of this set, because otherwise the limit is not defined by definition. And we have already seen what happens if you try to forcefully consider the limit of a function at a point which is not an adherent point. You can then get nonsensical results. Okay, so the proof here is actually the first exercise. See exercise 10.5.1. And now let us see the second version of L'Hopital's rule, which in fact we are going to prove. So this one is again L'Hopital's rule, but part 2. I don't really know the significance of this hat. I at least know that it is supposed to indicate some special type of pronunciation, but I don't really know about it. Let's see the statement though. This time let a and b be real numbers such that a is less than b. Consider functions f. Again we will have two functions, but this time, see, there we had the domain x which can be any subset. Here however, this interval, closed interval, that too, and g, both of which are differentiable. Differentiable on the entire interval. So you see that unlike the first version, here the hypothesis is much more stringent. It's much stronger because we are assuming differentiability of the functions not at a single point x naught but throughout the domain. Okay, so it's much more strong. Suppose that both f and g vanish at the left end point of our interval. So the role that x naught played over there in the first version, here that same role will be played by this left end point a of the interval. So we are assuming f and g to be vanishing at a, and the derivative of g does not vanish for all x belonging to the interval. So although g itself vanishes at a, but the derivative of g does not vanish at all. Okay. At every point in the interval, the derivative exists first of all because f and g are both differentiable everywhere, but it's not equal to 0 for g. Okay, something else is, I should not have stopped the sentence there, but anyway, let me start a new sentence. Let the limit, have to carefully write the limit here. Oh, so these are derivatives. So this limit exists and b equal to L, where L is some real number. Limit existing means being equal to some real number. Then, so these are the hypotheses. Then g of x is not equal to 0 for all x belonging to the open closed interval a comma b, and this limit also exists. Also exists and equals L. Okay, so many of the hypotheses as well as the conclusion, both the parts are like the previous one. So let us again go through this. A and B are real numbers and A is less than B. This makes the closed interval a non-degenerate interval. Okay, and f and g are real valued functions, both defined on that closed interval. And f and g are both also differentiable everywhere on this closed interval. Suppose additionally that f and g both vanish at this left endpoint, and that the derivative of g prime x never vanishes, nowhere in this interval. Finally, let the limit of the ratio of the derivatives f prime x divided by g prime x at a inside this open closed interval a comma b exists and b equal to a real number L. Then comes the conclusion, which has again two parts. The first part is that g does not vanish anywhere in that open closed interval a comma b. And the corresponding limit for the ordinary function value ratios f divided by g also exists and is equal to L. Alright. Now, why do we have the conditions like this? First of all, we need g prime x to be non-zero in this interval, but of course, we have it non-zero everywhere. For this, for us to be able to talk about this limit, because here g prime x is appearing in the denominator, and the set in which we are considering this limit is in fact this set. Alright. And for the second limit, in fact that's the main conclusion. We need g of x to be non-zero in this set. So we have that. That is the first part of our conclusion, and in the second part we are considering the limit, and that limit also has to be equal to n. So if you recall your application of L'Hopital's rule in actually solving problems, in fact you did not really use the first version, because what do you do when you apply this rule? You have a limit where you see a ratio of two functions, and you cannot immediately figure out how to calculate the limit. So what you do, you differentiate the numerator as well as the denominator. Now the previous version says that immediately you have to put the point itself there, f prime x naught divided by g prime x naught. This, however, rarely works. Most often what we do, we differentiate once, that doesn't work. We differentiate again, that may or may not work. So you may have to differentiate many times to ultimately get the answer. And this is the second version. Okay. So let us now see the proof. The proof actually is not very difficult. Although the proposition looks difficult, but the proof is not really that difficult. We just have to keep in mind that we have two things to prove, this and this. So this is proved first. There is in fact a remark here before the proof, but you can just see that it is nothing really that important. You can see the remark yourself. So in the first part of the proof, we have to prove that g of x is non-zero for all x belonging to the open closed interval a comma b. Suppose this is false. Suppose that g of y is equal to 0 for some y belonging to this. Okay. Now we are, because of this supposition, we are in a position to use the Rolle's theorem. How? You see, we have our function g, right? It is given that g is differentiable everywhere on its domain. Okay. In particular, if you restrict g to now, why did I take x there? It will be y. If you restrict g to this interval, then the restriction also, of course, is automatically differentiable. And because the restriction is differentiable, this is, it is also automatically continuous because differentiability implies continuity. This is continuous. And of course, if you do not think about the endpoints, this is differentiable. Do you get the flow? It's given that this is differentiable, hence this is differentiable because it is simply a restriction of G to this subinterval. Oh, and also note carefully that because y belongs to this, that means y is strictly greater than a. So this is a non-degenerate interval. But at the same time y is less than or equal to b, so this is a subset of this. That is why differentiability of G implies differentiability of this restricted function, which in turn implies its continuity. And also, of course, because G is differentiable on this open interval, on this closed interval, it's automatically differentiable on this open interval. Now, additionally, you have G of A equal to 0, which you already had, and your supposition gives you G of Y equal to 0 as well. So all these conditions are the hypothesis of Rolle's theorem. That means you can apply Rolle's theorem. So by Rolle's theorem, what will happen? The derivative of G at some point will become 0, and that some point will lie between A and Y. In particular, that some point will lie in this open interval. So let us now write that. These things, of course, are only for our understanding. So I can wrap this up. So, by Rolle's theorem, G prime, I do not want to use something which is not there in the text because you may be watching this video and simultaneously looking at the text. I want to use the exact same symbols. What is the point that they have? Okay. So if I am really using what the text has used, I should have called this X. It does not really matter, but I do not want to write something else causing unnecessary confusion. So this one I am going to call Y, or rather the author has called it Y. This is equal to 0 for some Y. For some Y belonging to the open interval a comma x. In our small discussion of why we are able to apply the Rolle's theorem here, you imagine x in place of y. Okay. So we now have a point like this. All right. But this is a contradiction. Why is it a contradiction? Because it was given that G prime is not vanishing anywhere on the interval a comma b. But here, of course, we have got a point y which is clearly in the interval a comma b because it's in this subinterval at which G prime vanishes. But this contradicts the hypothesis that this is not equal to 0 for all x belonging to a comma b. The author should have been rather careful about these things. Here we are using x as a variable, and here we are suddenly using x as a specific point. This may cause confusion. So instead, let me just make a small change. Let me just call this x prime. Okay. Yeah, now there is no confusion. So, our supposition is wrong, i.e. g of x is not equal to 0 for all x belonging to the open closed interval a comma b. Do not write closed interval a comma b, okay, because it is already given that g of a is equal to 0. Everywhere else g is not vanishing. Now next comes the limit. We next have to show that this limit is equal to n. And in showing this, we are going to use sequences, or more specifically the sequential formulation of limits. Proposition 939, I believe. And because we have to use that, let us recall that. Let's recall that statement. That statement was like this. X is a subset of R. F is a function from X into R, and X naught is an adherent point of X. That means it belongs to the closure of X. Then these two statements are logically equivalent. Oh, and we also need a real number L because we need the limit. Limit as X tends to X naught in E. Oh, I wrote E here now. So let me change this a little bit. Let E be a subset of X and X naught be an adherent point of E. Then the limit of F at X naught in E is equal to L. So this is one, and the second is this. For any sequence Xn in E such that the limit of Xn is X naught, we have this. These two statements are equivalent. So in order to show that a function has a limit, all you need to do is take any sequence in the set E, whatever the set is. In our case, this is E, okay. That converges to X naught. That means that converges to A. And show that the functional values of the sequential terms form a sequence which converges to that limit. If you show this, then this will be true. And if this is true, then this is also true. Okay, so we are going to use this. All right. And hence we write by was it 939? Yes. By proposition (939), it's enough to show that for any sequence, what have they called the sequence? Xn, I guess. Yes, and n varies from 1 to infinity. Okay, fine. Xn in this. Converging to A. All you have to do is match this with this. That's all. The sequence f of xn divided by g of xn converges to L. If we are able to show this, then that means we have our limit by that proposition 939 again. So let xn be a sequencing this converging to A. Okay. Now for each positive integer, because here the indices are all positive integers, we are going to consider a special function. For each integer n greater than or equal to 1, you define a function hn but how you are going to define this function is important, and it will be defined on this interval a comma xn, and it will be a real value function by this rule hn of x will be equal to f of x g of xn minus g of x f of xn. Can we do this? Note that each xn, no matter what the index n is, belongs to this set because this is the sequence in this set. So each xn is greater than a, and that is why this is a non-degenerate closed interval. Fine. And how have we defined the function? We have defined our function hn using f and g. So what you are looking at is simply a linear combination of the functions f and g, because g of xn and f of xn are constant. They are not changing with x. F and g, however, are changing with x. Now what can we say about this function? We note that since f and g are both differentiable on a comma b, they are both differentiable on a comma xn as well, because this is a subinterval of this a comma b. Moreover, hn being simply a linear combination of these differentiable functions is itself differentiable by algebra of derivatives. Hence, hn is differentiable on a comma xn, and this implies that hn is also continuous on a comma xn. Hence, hn is continuous on a comma xn and differentiable on open interval a comma xn. And you understand what I am trying to do. I am trying to create the hypothesis so that I can apply Rolle's theorem again. So what else do I need? I still need to show that hn vanishes at a and xn. Also, what is hn of a? Hn of a is f of a times g of xn minus g of a times f of xn, but recall our hypothesis, f and g both vanish at a. Yes, so this is just 0. And what about hn of xn? This is f of xn g of xn minus g of xn f of xn, again 0. That means we can apply Rolle's theorem on hn. So by Rolle's theorem, I can write here, right? hn prime of y is equal to 0 for some y belonging to the open interval a comma xn. Now look carefully. For each positive integer n, we are getting a point y in the open interval a comma xn at which hn prime y is equal to 0. This is happening for each n. So you are getting infinitely many sets which are all non-empty. The first set is the set of those points in the open interval a comma x1 at which the derivative of h1 vanishes. The second set is the set of those points in the open interval a comma x2 at which the derivative of h2 vanishes. All these sets are non-empty. So by the axiom of choice, you can pick one element from each set and that will give you a sequence. So by the axiom of choice, I don't know if in this proof axiom of choice is mentioned, probably not, but that is there in the background. By the axiom of choice, there exists a sequence yn such that yn belongs to a comma xn and hn prime of yn is equal to 0, or need to also mention for all n, for all positive integers n. Now let us actually calculate hn prime, because it's a linear combination of f and g, so you can calculate the derivative. Now, in fact, let's use this. Hn prime of yn is equal to 0. So what was our hn? Our hn is f of x g of xn minus g of x f of xn. So it will be f prime yn g of xn minus g prime yn f of xn equal to 0. So we can now manipulate this a little bit. F prime of yn times g of xn is equal to g prime of yn times f of xn. Alright. Now the next step is to divide both sides by g of xn and g prime of yn. Can this be done? Of course, you have to make sure that neither this nor this is equal to 0. Where is xn coming from? Each xn, you see, our original sequence is xn, right? And it was a sequence in the open closed interval a comma b. Now g only vanishes at a, and it does not vanish anywhere else. In fact, that was the first thing we proved in this proof. And no xn is equal to a, so that means g of xn is non-zero no matter what n is. Furthermore, it is already given that g prime does not vanish at all. Nowhere in our set closed interval a comma b does g prime vanish. So of course g prime of yn also is not vanishing. That's why we have this. Now next we are going to use the fact that each yn is in the open interval a comma xn. Where is that? Here. And we already know, in fact this is how we chose our sequence xn. Xn is a sequence that is converging to A. Now, since yn belongs to A comma xn, we have these inequalities, right? For all positive integers n. Since xn converges to A, xn converges to A and the constant sequence A of course converges to A as well. So by the squeeze test for sequences, yn trapped in between these two convergent sequences converging to the same value is also forced to converge to the same value. The squeeze test implies that the limit of yn is also equal to A. Okay. Now let us see what we have got. We are now looking at a new sequence, a sequence yn, which is also, because of these containments, this type of containments, a sequence in the open closed interval a comma b. That means yn is a convergent sequence here. And originally what we are given, we in fact are given a limit, right? That limit, however, involves the derivatives of f and g, not simply functional values. Since yn is a sequence in open closed interval a comma b converging to A, and this is what we are given. Limit as x approaches A in this interval of f prime of x divided by g prime of x is equal to L. So we have got a sequence of points in this set converging to the point at which we are considering the limit. So that means again we can apply proposition 939. Proposition 939 implies that the limit of f prime of yn divided by g prime of yn is equal to L. But this is that. So f of xn divided by g of xn is also equal to L. And this is what we wanted to show, right? We chose a sequence of points in a comma b which is xn, any sequence that converges to A. We wanted to show that the functional values of this quotient, of course, converges to L. And hence by proposition 939, again because that is a necessary and sufficient condition, we have our result. So, by proposition 939, we finally have this. And that completes the proof of the second version of L'Hopital's rule. And this also actually completes the section minus the exercises. So we will solve the exercises next Sunday. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.